Questa qui. Ok. Quindi, vabbè, uso il microfono perché vabbè, abbiamo un ritardatario, ma comunque. Così salutiamo.
Devo vedere che viene tagliato.
Sì, vabbè, allora Ludovica non mi vedevi, adesso comunque. Tanto chi ci ascolta da remoto e abbiamo invitato il professor Carlos Platas-Iglesias dell'Università di Corugna, Spagna, Galizia, e nell'ambito del programma di internazionalizzazione, quindi si ferma da noi per 2 settimane e quindi è qui per motivi di ricerca. Poi, quindi all'interno di questo periodo lui ha un paio di lezioni extra, quindi oggi una lezione dove darà un'introduzione generale ai metodi computazionali, quindi i vari metodi possibili e le loro applicazioni, mentre la settimana prossima, se verrete ognuno col vostro computer, vi darà da scaricare gratis un programma col quale potrete analizzare delle molecole semplici, tipo l'ammoniaca, l'acqua, vedere l'inversione dell'azoto e così via. Quindi provare a mettere in pratica. Tanto per avere insomma un'idea di questi strumenti, di cosa possono o come possono essere utili. Lui è un chimico inorganico, ma probabilmente l'argomento è molto multidisciplinare. So, yes, you can.
Okay, right. Thank you.
No, I mean, it's easy to follow Italian.
Yeah. Understood everything, I think. Okay. Thank you. So, we'll start by thanking Mauro for the invitation to visit Alessandria for these 2 weeks. It's a great pleasure. A bit hot, but well, still enjoyable. And well, as Mauro mentioned, the idea of this short course is to provide you a short introduction to computational chemistry. I was told that you have like quite different backgrounds, so maybe you had in the past some contact with computational chemistry or with quantum mechanics, maybe some others less contact. So I will try to be, very basics, and so it might be that for some of you, some of the things I will discuss will be rather basic, maybe for some others not. But the idea is that today you get like a broad view of the different methods that are available within computational chemistry. And after that, we will have a session next week that will be more practical. So we will use some software and do some small modeling of a few molecules, so that at least my objective is that by the end of these 2 sessions, you have an understanding of what computational chemistry can be useful for you, right? So this is the general idea. So going straight to introduction, in computational chemistry, you have basically 2 main families of methods, right? And all these methods have in common that they use mathematical approximations to address some chemical problems. These 2 families of computational chemistry methods are, on the one side, the molecular mechanics methods, which are based on the laws of classical physics, so there are no quantum mechanics involved. That means that, well, we can address many problems with molecular mechanics, but some others are out of reach, particularly when, handling or describing the behavior of electrons is important. For instance, if you are forming and breaking bonds, let's say, that's a difficult problem for molecular mechanics. The advantage of molecular mechanics is, however, that you can model very large systems because the method in general is cheap computationally, right? So you can handle, like, for instance, huge proteins and things like that with molecular mechanics. Then a second group of methods are the methods based on electronic structure theory. That means in quantum mechanics. And here, there are also several options that maybe you've heard about. You can have, for instance, semi-empirical methods. So the name is already telling us something, right? So these semi-empirical methods use empirical parametrization to solve the Schrödinger equation, right? Because these are methods based on quantum mechanics. And this, of course, simplifies the calculations, so they are cheaper. You can also address or model compounds that are larger, right, with more atoms in general. Then you also have ab initio methods. These are purely based on quantum mechanics and just a few constants, right? Like the mass of electron and proton and stuff like that. So a few physical constants and quantum mechanics. And there are, of course, also different methods that have been developed. Probably the simplest one is the Hartree-Fock method. But from there are many other ab initio methods that are much more sophisticated and that can provide really very precise results for complex problems, right? But they are also generally very expensive computationally. So quite often you can only address, very small systems with very expensive computational methods. And then a third class of methods based on quantum mechanics is, are the density functional theory methods that you have heard about for sure, right? Even colloquially when we talk, let's do some DFT, right? But DFT is not just a method, right? It's just like a group of different methods, and there are different possibilities within DFT. And we will, later on, briefly describe the different DFT approaches that you can use. So these are the two main classes of methods. You can have also calculations using hybrid approaches. For instance, you have let's say a big protein with a metal in an active center, and you are more interested in how the active center is working, right? So you can maybe model that active center using DFT or some electronic structure method, and then use molecular mechanics for the rest of the system, right? So that's also possible, and sometimes it's even necessary. So this is, computational chemistry is really a field that is expanding really quickly. And this is first because the computers are getting faster and faster. So the computational capability is higher and higher. And also because the algorithms and the software that we need to use for our calculations improved really a lot. So in the last, I would say, couple of decades or something like that, this improved, but dramatically. So that now it's possible to do really very accurate calculations sometimes for relatively large systems and with user-friendly programs also. So this is always, have the pros and cons, so that you don't need to use, the software. You don't need to be really a very extremely well-trained quantum mechanical guy, right? But on the other hand, you can also do mistakes, of course, if you work in a black box mode. But now definitely computational chemistry is much more accessible to, I would say, to anyone that is interested in this field. What kind of problems can we address with computational chemistry? Well, virtually everything, right? Because any property of any compound will eventually depend on the electronic structure, right? So if you describe the electronic structure, you can, in principle, address any chemical problem with more or less accuracy. Some examples for equilibrium geometries, of course. So what is the minimum energy structure of your system? not only for energy minima, but also for transition states. So if you can model transition states, you can model reactivity, you can extract kinetic parameters, even exchange rate or rates, right, for any chemical process. You can calculate dipole or quadrupole moments, for instance, vibrational frequencies, so that you can, this can help analyzing your infrared or Raman spectra. You can calculate also NMR spectra. For instance, so RMN, just as that's the Spanish spelling, sorry. But so it's NMR spectra. You can model excited states. So that means that you can also, in principle, calculate absorption spectra and even fluorescence spectra, of course. Well, reaction rates, you also can obtain thermochemical data, so you can estimate enthalpies and entropies and so on. So, and many other things that you can do with computational chemistry. So these are just a few. By the way, I didn't mention, but if you have any question at any time, please stop me. I will try to answer, okay? So for the first family of methods, you will see some equations, but don't be scared if you are not very much into physical chemistry. So we will just try to have a look to the equations and try to understand a little bit, right? So that we have a flavor of how these computational methods work. So in molecular mechanics, we always have the so-called force field, okay? So we are working with classical physics. So somehow we have to describe the energy of our system, all right? And you see that the energy, that's a force field, right, that you see there on the top. So the energy of a system is generally parameterized in terms of different terms that account for bond distances, bond angles, so if they involve 3 atoms, right? Dihedral angles, if they involve 4 atoms, and then some additional terms that you have. The last term that you have there accounts for electrostatic interactions and van der Waals interactions. So altogether, interactions between non-bonded atoms, right? And there are many force fields that have been defined, of course. I think I took this one from Amber, which is one of the programs. So just so you can see how a force field looks like. You see that for bonds, for instance, you have an harmonic potential to describe your bond, and that makes sense, right? So you have a distance between the 2 atoms, which is R, and an equilibrium distance, R EQ, right? And that has been parameterized. So you see that if R, so if the distance between the 2 atoms varies from the equilibrium distance, your energy will increase, right? As simple as that. And of course, that energy penalty will depend on the force constant that is multiplying there, R minus R EQ. Okay, so that's just an harmonic potential. And the same for the angles. So it's just the same expression, but instead of distance now, you have an angle involving 3 atoms. And for the dihedrals, what you have is a cosine function in general, so that you have a dihedral angle phi, and as you move your system from this dihedral angle, then also your energy increase. Actually, there is, I think there is, there is an n that should multiply phi there, that is missing, and that n will give you the number of maxima and minima that you have on your energy profile, right? And well, finally, you have this Lennard-Jones potential. So you have a repulsive term there with R to the 12th power. So that will operate when you have very short distances because of the 12th power. And then you have an attractive term there with an R to the 6th power dependence. And finally, you have some, the electrostatic interaction, right? Okay. So it's rather simple, actually, right? How a force field looks like. Now, our force field will require parametrization, right? So somehow we have to indicate what are these equilibrium distances, those force constants for distances and angles and so on. So that requires parametrization using experimental data, of course, right? So it's obvious that the force constant will be different for a carbon-carbon single bond, for a double bond, for a triple bond, and so forth, right? So generally, when you are going to start a calculation, you need to provide some set of coordinates where your nuclei are supposed to be, right? So the structure. And you have to describe your atoms in terms of atom types according to that force field, to that parametrization, right? So you have to say, I have a carbon here, and this is an sp2 carbon, right? So that the program will pick up the right parameters for that specific atom, right? And the same for any other atom. Is not the same also a mine, right? An sp3 carbon that an imine, an sp2 carbon or whatever, right? So you always have to indicate coordinates and atom types, right? And you have to select a force field. So the advantage of this, using force fields is that this is very cheap, as I mentioned before. So you can handle very large systems, right? What is the problem of parametrization? Generally, your model is valid or will provide reliable results for systems that are somehow related to the systems used for parametrization. Is this clear? So sometimes, you have to be very careful just selecting a force field that was parameterized with organic molecules, because maybe you put there a metallic ion or whatever, and you get some results, but maybe that they make no sense, right? So when you use molecular mechanics, you are limited by the quality of your force field and how it was parameterized. So force fields cannot be applied universal, right? That I think that makes sense, right? Okay, so that's the expression of an energy for a typical force field. Then you can apply the Newton equations of motion, right? And that allows you to study dynamics. Well, I forgot that it had this second slide. This is, it's very easy to understand. So that's the harmonic potential for a distance on the left, for an angle, and this is how the expression for the energy of dihedral angles look like, right? So the number of minima depends on m. That should be multiplying phi over there. So now you can use the Newton's equations of motion. So force, mass, and acceleration, right? So that's the acceleration is the second derivative of the position with respect to time, right? And that equals the derivative of the energy with respect to the positions of the atom, right? So from here, in principle, you can express the energy of the systems depending on the position of the nanoparticles, that is the position of the nuclei. And then we are relating the derivative of the energy with how the system is changing with time, right? So that means that we can do molecular dynamics using force fields, right? And this is relatively simple, right? The problem is that this differential equation has no analytical solution. So we need to select also some integration methods, some proximate integration methods. So if we are going to run molecular dynamics using a force field, so using molecular mechanics, we need to select the force field, some initial conditions, and also an integration method, and that is generally simply implemented in the software. Okay, so this may be very useful, for instance, to if you are modeling, let's say, flexible molecules, and you have potentially several energy minima, right? Sometimes it's a very good idea to to run some molecular dynamics at the beginning to generate several starting structures that you can afterwards maybe model at a higher computational level, right? But in that way, you screen your conformational space, and at the end, you can be, well, pretty sure that you have reached, you know, the global minimum structure for your system. So this is all I will say about molecular mechanics methods. So just trying to see how they are defined and also the limitations that they have, right? Well, I have to say, I didn't say it at the beginning, but I'm not actually a theoretician at all. So I'm more an experimentalist that is using computational chemistry to address some problems that, well, I'm interested in, right? But in general, I use electronic structure methods. And well, of course, these methods are all based on the Schrödinger equation that cannot be solved exactly, except for a few systems. But the fact that it cannot be solved exactly, that there is no analytical solution, doesn't mean that we can have very good approximations, right? So even if the solution is not an exact solution because it's not obtained analytically, you can have really, some very often, very, very good approximations. Right? Yeah, I think that's briefly summarizes this, this slide, right? Of course, yeah, depending on the method, if you need more accurate results, then the computational cost will also increase, of course. Well, in general, these electronic structure methods rely on three different approximations. One is the Bohr-Oppenheimer approximation that you have heard about, and that leads to the concept of potential energy surface. I will illustrate this in a moment. Then the second approximation is expressing the wave function in terms of Slater determinants. And well, this is known as the method, actually. So the different electronic structure methods differ in the way that they define the wave function in terms of Slater determinants. And then the third approximation is the representation of molecular orbitals in terms of some predefined functions that we call basis sets that are essentially atomic orbitals, or they look like atomic orbitals in a way, right? So basically, these are the three approximations, right, that we are doing whenever we are using an electronic structure method. Well, so let's go to the first one that is very simple, right? So you already know this, I think. So the Bohr-Oppenheimer approximation. So basically our wave function that should come from resolving the Schrödinger equation is a function of the coordinates of all nuclei and all electrons, right? But the electrons are much heavier, are the other way around, sorry. Nuclei are much more heavier than electrons, right? So the mass of a proton is around 2,000 the mass of an electron. Right? So that means that these two particles are moving in different time scales. Since nuclei are heavier, they move more slowly compared to electrons, right? So if we were a nucleus, right, and we would be in a certain place and look around, we would see electrons like, moving very quickly around us, right? And since these two particles are like moving in very different time scales, we can, to a reasonable approximation, separate the two motions, right? So this means that we can express our wave function in terms of the electron wave function and the nuclear wave function, right? So we can separate the two of them. Actually, if we have like a look at the Schrödinger equation, well, you will see it's rather easy to understand. No? So it's not very complicated. So you have this Hamiltonian there that has some kinetic energy terms and potential energy terms, as you see T, V. And basically, they have, well, the Hamiltonian is written in atomic units, right? So in atomic units looks like this, but you can even find, slightly different expressions depending on the units, right? So the first term is the nuclear kinetic energy, right? So and that term resembles the equation for the kinetic energy that you get in classical physics, right? So it's 1/2 the mass times the square of the speed, right? So that's the kinetic energy of the nuclei. The second term is the kinetic energy of the electrons. So instead of the mass of the nucleus, you have the mass of the electron, of course. Then here you have the nuclear repulsion energy, right? That makes sense. Positive and positive, they will have some electrostatic repulsion. Then you have the attraction between nuclei and electrons. And you see that the expression resembles the Coulomb expression for electrostatic energy, right? And finally, you have the inter-electronic repulsion, right? And what you have some here is derivatives with respect to the position of the particle. Okay. So it's not very difficult to understand, at least in this qualitative way, right? So applying the Bohr-Oppenheimer approximation, we can separate the electronic and the nuclear part, or in other words, we can assume certain positions for the nuclei and solve the Schrödinger equation for the electronic part, okay? And then maybe we can change the position of our nuclei and solve it again and calculate the energy and move again and calculate the energy, right? Now you are seeing how you get a potential energy surface, right? For instance, for a diatomic molecule, so that's, I think this is for, is it not written? Oh yes, it's mercury 1 bromide, right? Just the diatomic system, right? So there, since you have two atoms, the only thing you can change is the distance, right? So yes, you assume that your distance is somewhere around here. You solve the Schrödinger equation for the electronic part and you get an energy that is like coming here. Then you shorten the distance, you see that your energy, is going down. It passes through a minimum that corresponds to the equilibrium distance, right? Or to the distance at equilibrium. And then the energy is increasing because of the internuclear repulsion, basically, right? So this would be the potential energy surface for a diatomic molecule. Of course, if you have more atoms, you have multi-dimensional potential energy surfaces, right? Because you have many variables that you can define, but you could still like select one in which you are interested and then maybe optimize the geometry constraining that particular bond or angle or whatever, and calculate the energy and define a potential energy surface. Hope it makes sense. Yeah, you have questions? No? Okay. If you don't have questions, we move forward. So you know about this, right? So the problem with the Schrödinger equation is that it cannot be solved as soon as we have 2 electrons or more because of the this term that contains the inter-electron repulsion. Right? So we need to do some approximations. So the second approximation after the Bohr-Oppenheimer approximation is how to express the wave function in terms of Slater determinants. Okay? And well, a Slater determinant is given there. So here, and it's also easy to understand. So phi there would be a molecular orbital, okay? And alpha is a spin function, and beta is another spin function. Alpha is just spin up, beta is spin down, okay? So you see that in this determinant, you have a collection of molecular orbitals from phi1 to phi m, multiplied by these spin functions, alpha and beta, okay? So at the end, this determinant will contain all possible combinations of molecular orbitals and occupations by the electrons of your system, okay? So you just need to define these molecular orbitals so that the energy and the occupation, so that the energy of your system is minimized, okay? And you could like use a single Slater determinant to describe your system. And this is what the Hartree-Fock method is doing, right? So it's using a single determinant. So if we go to the expression above, we have a linear combination of different Slater determinants, P0, P1, P2, and so on, multiplied by some coefficients D0, D1, D2, and so on. So in the Hartree-Fock method, we would stop at the first term. So D0 times PO, and that would be the expression of our wave function. In practice, that means that we are not describing instantaneous interactions between the electrons, what we call electron correlation. So in the Hartree-Fock method, due to this, let's say, oversimplification of taking just the first Slater determinant, each electron is like seeing and reacting to an average of the remaining electrons, okay? So electron correlation, instantaneous interactions between the different individual electrons are not taken into account. Then more sophisticated methods are, methods that include other Slater determinants. For instance, if we take an atom of neon, the first determinant, the one that the Hartree-Fock method is using, would describe that electron configuration that is over there, right? So it's 1s2, 2s2, 2p6, which is the electron configuration for neon, right? Other methods, more sophisticated ab initio methods, would include additional determinants. And the second could be, for instance, that one over there, corresponding to that electron configuration, 1s2, 2s2, 2p5, 3s1, which for us is obviously an excited state, right? In terms, if you think about electronic configurations. But of course, very likely, the contribution of that second determinant will not be very high, right? So that essentially, sorry for going back. So our coefficient D1 probably will be small, but still that would improve the description of our system by introducing, electron correlation, right? And of course, we could keep on adding determinants, but we have to stop at a certain point. Otherwise, we will have really a huge number of combinations, right? But there are, let's say, methods that can consider just a few of the combinations that we are interested in to describe our system, okay? But essentially, this is what ab initio methods do, right? So this is a way of introducing electron correlation. Actually, electron correlation is defined as the difference in energy between the Hartree-Fock solution and the exact solution of the Schrödinger equation, right? So electron correlation considers these instantaneous interactions between electrons with the same spin and opposite spin, right? Well, So there are, as I mentioned before, different methods that use different or more than one Slater determinant, right? And they differ basically on how to define the number of determinants and so on, and how to calculate also these coefficients that are multiplying the different Slater determinants. Okay, so far, we've been a little bit of molecular mechanics and electronic structure methods based on, let's say they are called wave function methods, right? Because they were basically based on the wave function. And the way to improve those methods is to improve the wave function, increasing the number of Slater determinants, right? Good. Within electronic structure theory, we would have another class of methods that are the DFT methods, okay? So instead of working with the wave function, DFT works with the electron density. So the approach is somewhat different. Okay? The thing is that with DFT, we can introduce to a certain extent electron correlation, at least compared with the Hartree-Fock method. The computational cost is not really much higher than Hartree-Fock. So you can run calculations in pretty large systems. And well, so if the computational cost is not very large, then it provides much better results than Hartree-Fock. So actually, Hartree-Fock is not used anymore, right? If you read papers dealing with computational chemistry, no one is using Hartree-Fock anymore unless you want to do some particular, you are interested in some particular effect. But in general, no one is using Hartree-Fock because DFT is much, much better with essentially very similar computational cost. So DFT methods are based on this Hockenberg-Kohn theorem that states that all properties of a system, the energy and related properties of a system, can be defined by the electron density, right? Actually, the electron density is described by the functional, which is essentially a function of a function, right? Well, the electron density actually can be defined as, or is defined as it is shown here, there on the top. So it has to be with the square of the wave function, right? Because that's the probability, right? According to quantum mechanics. So if you integrate that all over space, you get the electron density. And then, well, the Kohn-Sham equations that are behind the DFT machinery arrive to this expression there. So actually, all the mathematical treatment behind DFT is quite hard, I would say. Right? So it's not like straightforward. But still, what you have there is an expression that involves the energy of the system and the wave function, then kinetic energy term, and then this effective potential. And that effective potential that describes the potential energy of your system contains this term that accounts for the nuclear interactions. And then this term that depends on the electron density. So this is accounts for electron-electron interactions. And this exchange correlation potential, which contains describes the interaction between electrons with the same spin and opposite spin, and therefore incorporate to a certain extent electron correlation. Okay, so this is the basic thing, and that exchange correlation potential is defined as the derivative of the energy with respect to the density, right? Anyway, so with DFT, basically we are working with electron density. There are many DFT methods because that theorem states that the energy in all properties of a system can be defined by the electron density that is described by a functional. But it is not telling anything about the nature of the functional, okay? So there are plenty of functionals, so functions of the electron density, and therefore there are many DFT methods, but many. So we should be also very careful on selecting, when we are doing DFT, a good functional because of many reasons. So there are some functionals that perform better for some specific problems than others. And well, many functionals have empirical parametrization also. So that means that they perform better also for some specific problems. And so this is also one of the problems of DFT, right? That there is no one universal DFT method, because you have many functionals that perform better or worse for specific problems. So before doing some calculations for some specific system, we should maybe go to the literature, read a little bit, see what kind of functionals people is using for that specific problem, and then decide which one to choose, right? Anyway, just a brief description of the different functionals. So there are essentially, how many are they? 6 types of functionals. So the first family is based on the so-called local density approximation. You should not use that. I mean, they were used at the very beginning of DFT, right? And well, they work quite well sometimes for describing solids. So metals and semiconductors and stuff like that. But in general, for molecular problems, for instance, they do not work very well. And they are based on the local density approximation. That means that they depend only on the electron density at a given point in space, right? So our functional is a function just of the electron density, okay? Then the second family is the functionals that rely on the generalized gradient approximation. So that means that the functional depends on the electron density and also on its gradient, okay? And that provides in general a better description of the electron density, okay? So it's not only the density at a certain point, also how it's changing. Then a third family would be the meta generalized gradient approximation. So there is a term accounting for the kinetic energy density as well. Then we have hybrid functionals that can be hybrid GGA or hybrid meta GGA as well. So that complicates a bit more. And these functionals, these hybrid functionals include some mixture of Hartree-Fock exchange. So these are the main families, the first 4. And then we have, let's say, newer functionals, for instance, double hybrid functionals that introduce some perturbation treatment to a second order, so that they provide, in general, more accurate results, but they are much more expensive. So from 1 to 4, that's affordable, you know, for like Hartree-Fock almost, or a little bit more expensive, but not very much. Double hybrid functionals that are much more expensive. So if we have a large system, then probably we cannot afford double hybrid functionals. And then another family of interesting functionals is the long-range corrected functionals, which generally incorporate some empirical dispersion corrections. So if you want to study weak interactions, for instance, or maybe anions, which generally are quite expanded and things like that, then it may be a good idea to incorporate these long-range corrections, right? So that you can get more accurate results. And this is, well, probably you are not, if you are not doing computational chemistry, you are not familiar with these names, but maybe you've heard about B3-LIP, right? B3-LIP is probably the most popular functional that is used actually is the first one that people is choosing even quite often without even thinking a little bit, right? If it is the right one or not. So this is just, different functionals that are commonly used. And in some cases, the percentage of Hartree-Fock exchange that they incorporate. So basically from top to bottom, they go from simpler to more elaborated, let's say, including some long-range corrected functionals, right? So there's still a lot of people working in developing functionals because, as I mentioned before, there is no universal functional, unfortunately, that performs really well for any chemical problem. But maybe it will come in the future. Okay, so we have covered two of the three approximations, right? We have covered Born-Oppenheimer approximations and the method. So how to describe the wave function in terms of Slater determinants. So the third approximation is how to describe molecular orbitals that generally are defined as linear combinations of atomic orbitals, not really atomic orbitals, but functions that resemble or are similar to atomic orbitals, right? Good. And these molecular orbitals, the molecular orbitals are within the Slater determinants as this phi function, right? So phi would be expressed as a linear combination, as you see there in the equation that you have in the middle, as a linear combination of some functions that resemble the atomic orbitals, these C that are here, right? I think that's C, or I'm always confused with the Greek letters, but okay. And there are some coefficients there in our linear combination, right? So whatever the method we use, we need to find out the values of those coefficients, because those values will indicate how the molecular orbitals are defined, right? Okay. And that's generally done using the SCF calculation. SCF stands for self-consistent field. And that's like an iterative method, actually. So the process is you have an initial guess of what your coefficient C will look like, maybe doing a simple semi-empirical calculation or something like that. Well, the program is doing that for you, right? And then from this guess, then the coefficients are changed in an iterative way and calculating the energy using the variational principle. So until you reach a point where the energy is not lowered anymore, so that you have your definition of your molecular orbitals. And that's self-consistent because those coefficients will always give these molecular orbitals and the other way around. So starting from those molecular orbitals, you will end up with those coefficients. Okay, so that's something that the program is actually doing for you. And of course, you see that we have these C functions, these so-called basis functions. And the accuracy of our calculations will also depend on these basic functions, right? How accurate they are and how many we incorporate, right? And that's overall, these molecular orbitals are therefore expressed as linear combinations of basis sets. Basis sets are this description of the atomic orbitals with some certain functions, right? That could be Slater functions or Gaussian functions, but they resemble atomic orbitals, okay? So the thing is that we can add more or less basis functions to our basis set so that we can improve the description of the system, right? For instance, one of the simplest basis set that you can use is that STO-3G, right? That means a Slater type of orbitals approximated with 3 Gaussian functions. Okay, so the basis set is constructed with Gaussian functions, not with, let's say, Slater functions. And what was done to develop this basis set is to fit the Slater orbitals with 3 Gaussians. Okay, and so as a linear combination of 3 Gaussian functions. Okay, with some coefficients that were optimized so that the fit is the best possible, right? And that's the minimum number of Gaussian functions that you need to have a reasonable fitting, right? With less, you simply cannot fit the Slater orbitals. So a way to improve your basis set is adding more primitive functions, so more Gaussian functions, for instance, to your system, so that you end up, for instance, with split valence basis sets. Split valence means that, for instance, for let's say a carbon, so you have 1s2, 2s2, 2p2, right? So for your valence s and p orbitals, instead of using one set of Gaussian functions, you use 2 sets. And that improves the description of your molecular orbitals, right? And then you can even go further and use with the so-called triple Z basis sets. So you have 3 sets of functions for your valence orbitals, and maybe for your core orbitals, it depends, right? So that's a way of improving your basis sets, including increasing the number of functions. You can also use polarization basis sets or polarized basis sets. So that means, for instance, if you take again carbon, so for a 2s or a 2p orbital, you need an angular momentum that would be 0 or 1, right? But you could maybe add functions with a higher angular momentum. For instance, you could add d functions, okay? Even when in principle, the orbitals should not play an important role for carbon, right? Because they are supposed to have high energy, but still adding d functions polarizes your basis function. That means that the orbitals are somehow allowed to change shape. And that also improves the description of your system. Actually, virtually in any calculation, one is using polarized basis sets, right? Maybe in the old times, but nowadays, you always incorporate polarization functions. And this type of basis sets, that's indicated by this star. That star means that you incorporate polarization functions. You can also add diffuse functions. So that means that, well, they are like S-type of functions, but they decay like slowly when you increase the distance to the nucleus, right? And so that this is good to also to when you want to model weak interactions, for instance, or anions also that expand a lot, then it's a good idea to add diffuse functions to your systems. In some basis sets, they are added already by default, right? So in general, here you have the different types of basis sets, right? So it's just double set or split valence, triple set, then you have polarization functions, you can have diffuse functions. And then another thing that I will mention is, relativistic effects. We have to be careful with that. So I will not enter into that. So you can incorporate explicitly relativistic effects in your calculations if they are relevant. So that when you have heavy atoms, let's say beyond the 4th period, let's say, right? Beyond the 4th period of the periodic table, you should be aware that inner electrons are moving at speeds that are approaching the speed of light, and that has an effect on the energy of the orbitals and so on, right? So somehow you need to incorporate relativistic effects. So if I work, for instance, in coordination chemistry, right? So in coordination chemistry, this is essential unless you are working with first row transition metals, maybe, right? But below that, you always have relativistic effect. So at this point, I just say that be careful if you have metals, right, or heavy elements, so that somehow you consider relativistic effects. In practice, and we will do it in one of the exercises next week, for some problems, you can use the so-called effective core potentials, and that's very simple because you can select them like a simple basis set. But actually, when you incorporate these ECPs, you are describing with a basis set only the outer electrons, so valence electrons in general, and then the core electrons are not described in an explicit way, so they are replaced by some pseudo-potentials, right? And these pseudo-potentials were parameterized using, for instance, thermodynamic data, ionization energies, or things like that. So at the end, they incorporate relativistic effects, although in an indirect way, because they were parameterized to experimental data, right? So that's the way of, a simple way of incorporating relativistic effects, at least in simple calculations. In some other cases, you need to do more sophisticated approaches. So a bit more of basis sets. So what you see there is the general expression of a Slater orbital and the general expression of a Gaussian function, right? So you notice there that in the Slater orbital, you have E, the power of R, right? Well, multiplied by that alpha coefficient. And in the Gaussian functions, you have E to the power of alpha times the square of R, right? So that makes the shape of the functions a bit different, you see? You see that here in red, a Slater function is like more sharper. And Gaussian functions, you've seen Gaussian functions many times, right? You know that they are like rounded, right? So, well, in practice, most of programs use Gaussian functions to describe basis sets, and most basis sets incorporate Gaussian functions instead of Slater orbitals. And this is apparently because Gaussian functions are easier to handle for the algorithms that the programs are using. But it also creates maybe some problems, particularly because it's not that the Slater orbitals are more picky at the nucleus, but they decay like slower, right? And the Gaussians like decay faster. So yeah, probably that's one of the reasons why you need to add also diffuse functions that I mentioned before, right? To like, balance this a little bit, okay? And then you see in this expression, you have these x powers of Lx, Ly, and Lz, and that gives you actually the type of orbital that you have. So that Lx plus Ly plus Lz gives you the angular momentum quantum number L, right? So for an S orbital, the three Lx, Ly, and Lz would be 0, right? So you don't have dependence on X, Y, and Z because S orbitals are spherical, right? And if you have a p orbital, then you have actually 3 orbitals. So you would have a 1 here, 0, 0, or well, the 3 combination, right? And then you have obviously spatial orientation. Good. Well, this is a bit more about the basis sets, just taking the terminology of Poppel's basis set, which is a Nobel Prize in chemistry for his contribution to quantum mechanics. So he developed the classical basis sets that have this terminology like 6, DAS 31G. So that 6, for instance, indicates that are 6 functions or a function with 6 Gaussian primitives. So it's a linear combination of 6 Gaussian functions to describe the inner orbitals. Yes. So one is in carbon, for instance. And then you have 2 basis functions. One that is a linear combination of 3 Gaussians, and the other one that is a primitive Gaussian, a single Gaussian, to describe the valence selections. So that would be 2s and 2p for carbon, for instance, right? So this is the terminology. And this 6311G, then you add additional functions to the valence, right? And so on. Then you can have polarized and diffuse and so on. So that's the terminology of these Popol basis sets that were the most used basis sets. They were developed, I think, by the 1970s or something like that, 1970s, even 1980s. And they were very popular all through, the computational chemistry field until maybe, would say 10 years ago. Now they are a bit out of fashion. So there are newer basis sets. For instance, you have the Dunim basis sets. They have a different terminology, but basically they have this, that V represents valence, and that N is double valence, triple valence, quadruple valence, and so on. I think they are defined as up to 5 or 6, I'm not sure. And they are very accurate. While a triple valence, this CCPV-TZ equals a very much polarized Popol basis set. So this one that you have here, that includes polarity D and F, polarization functions, and so on, right? So this in quality is approximately that triple set basis set of the Dunim family. But you still have the quadruple and quintuple and so on, right? And a nice feature of these basis sets is that they are like consistent. So you can run calculations for the same system using in basis sets increasing the value of n, and you would see how your energy is decreasing, right? Like in this plot. Okay. So this is very useful if you want, for instance, to extrapolate your energy to an infinite basis set. So by definition, you introduce an error always because you are using a finite basis set, right? And you cannot do anything against that. But of course, you can add more functions, but you will always have a limit, right? But in this way, since these basis sets are consistent, you have a way, you feed this to an exponential so that you can extrapolate your energy to the full basis set limit. And sometimes this may be useful. Well, how about the computational cost? Well, these are some ab initio methods. So Hartree-Fock, MP2 is perturbation method. And then you have other methods that are even more sophisticated. And all these methods rely on, wave functions, on improving the wave function, right? So they are not the FT. But you see that the scaling, it doesn't matter. I mean, not important about the methods, but the important thing that I want to show here is that the scaling of the method is not linear at all with the size of the system or with the number of basis functions, right? At all. So for instance, Hartree-Fock scales with the square or the third power of the size of the system. But MP2, for instance, with the fifth power. Okay, so that's really a lot. And more sophisticated methods, even with the seventh power, right? So that means that with certain methods, you can afford studying quite small systems very accurately, right? But small systems with a few atoms, maybe 10 or 20 atoms only, right? With some other methods, however, you can go to very large systems. So this is, well, some data there. So a threefold increase of the size or the basis set implies multiplying the cost of an MP2 calculation 243 times, right? So that's really a lot. And the twofold increase, so from ethane to butane, increases the calculation of the CCST calculation 128 times, just doubling. So we should have this in mind also, although, yeah, computational capabilities are increasing and algorithms are becoming better, and there are also approximations that have been developed that also help, right? So this is just a scheme of how we could work using computational chemistry. Well, this is meant basically for working, with modeling molecular systems. This is what I do in general, right? So basically, you need to start by creating some starting geometries. That's the first thing. Right? So you need, as an input for any software, you will always need some initial positions of your nuclei. So you have to create a starting geometry. And there are different softwares that can help you on this. Then, yeah, you need to make sure that your starting geometries make sense in a way, and also that you have explored the conformational space, particularly if you have flexible systems. That's very important. So sometimes it's a good idea to perform some geometry optimization at a low level, right? So that the computational cost is not very high. But you generate a set of optimized geometries, right? That will help you exploring the conformational space. Then from there, you can just disregard the structures with high energy, with very high energy, and perhaps optimize with a higher computational model a few of the structures that maybe have similar energy, right? Those with a reasonably low energy. And from there, you have explored, in principle, the conformational space. And this is very important. Well, I didn't mention, but the way that a geometry is optimized is generally by performing first derivatives of the wave function with respect to the nuclear positions. Because if you have a minimum, right, your first derivative should be 0, right? So what the program is trying to do is just to move the nuclei, calculation the first derivative with respect to the nuclear positions, and try to reach values of 0 for all these derivatives. So that's the way of optimizing the geometry that the program is doing for you, right? And then once you optimize, you should do a test to check whether you really have an energy minimum. And that comes from the second derivatives. So that if your first derivative is 0 and your second derivative is positive, you are certain you are in a minimum, right? So that's another thing that we need to do. So after the optimization, we need to calculate second derivatives with respect to the nuclear positions. And that corresponds to vibrational frequencies, okay? The second derivative is actually the vibrational frequency. So this is why here you see frequency calculation. So once you have optimized, you need to do a frequency calculation and check that all your frequencies are positive. That's very important. And if they are positive, they should resemble what you would expect in the infrared spectrum, right? And you could afterwards, with software, inspect the movement of nuclei for each vibration and see if that matches what you expect, right? So if you have a carbonyl, you expect some, stretching around 1,600 reciprocal centimeters, right? So this is something you should always do unless unless there is a good reason for not doing this. For instance, perhaps you are interested in running some calculations on an X-ray structure, and you are not interested in optimizing, then you skip the frequency calculation because you will get negative frequencies for sure, right? That means that you will be somewhere in a potential energy surface, not in the minimum, okay? So that you may be interested in, for some specific cases, for instance, to model something with an X-ray structure, perhaps you want to optimize only the position of the hydrogens, because they are not really, the position of hydrogens are not really determined very precisely by X-ray, right? So maybe you just optimize hydrogens and you use this geometry because you are interested in, you know, keeping the structure that you have in the solid state. But otherwise, whenever you do an optimization, you need to do a frequency calculation. Well, by the way, also when you study reactivity, it's very important to run the frequency calculation because a transition state is called a saddle point, is characterized by just one negative frequency. So all of them should be positive, but one that should be negative. And the displacement of the atoms for this negative frequency should give you or connect the reagent and the product, right? So when you study transition state, we will do it next week, okay? So you have reagent product. If you model the transition state, you need one negative frequency, and the movement of nuclei in this should like connect reagent and product, okay? So this is a test you always need to do also if you study reactivity. Well, at this point, you have a collection of structures, one or more structures that are well characterized. So you have your local, some local minima maybe, and some global minima. Sometimes you have isomers or whatever, so you even have populations of two species that are significant. So from calculations, maybe you can understand this and maybe assign them or whatever. And then generally, well, it's quite common. Ideally, you would like perform everything with one method, right? So optimizing frequency and calculating properties, but that's not always possible because calculating properties is quite often expensive computationally, right? So you cannot afford that method for optimization, or you would like be calculating forever, right? So it's quite common that once you have your structures that are in principle good models of your system, then you use some more sophisticated methods to calculate properties, right? And at this point, it's important to like think what kind of features are important for your system, right? Or for your specific problem. For instance, well, the basis set, do you have a large enough basis set so that you can calculate with accuracy your problem, whatever it is, for instance, NMR shifts, right? So my basis set, for instance, accurate enough close to the nuclei, because I'm going to calculate the nuclear property, right? The chemical, the NMR chemical shift, for instance. Or are relativistic effects important? So that's something you should also ask yourself. Or solvent, right? So there are also different models I didn't mention here, but there are different approaches to consider solvent effects. So one, the brute force approach would be adding solvent molecules around your system, right? You are working water, let's say, so you have your molecule and you add water molecules around to try to mimic your solution or your system in solution, right? But of course, that will increase a lot the computational cost because you are adding more and more atoms all the time, right? And also your system will become more complex in terms of the number of minima that you have in the energy, the potential energy surface, right? You add so many molecules that you will have plenty of minima. So it's hard to be sure that you are in the global one. And then there are other, well, alternative models that are not explicit. So you don't add explicitly solvent molecules, but you have somehow with electrostatics and so on, you can model to some extent solvent effects. And that sometimes is important, right? So you could maybe optimize a molecule in the gas phase, so no solvent, and then include some implicit model, for instance, for the optimization, and you end up with, observing quite significant effects, right? So that's another important thing. While the functional I mentioned before, that's also important to be sure that the functional you are using works well for your specific problem. Integration grids, for instance, in DFT, you need to perform integration in space. So you define a grid, a three-dimensional grid, where you selecting the points in space where you integrate, right? And by default, the software generally assumes that it constructs a grid with a given number of points, but maybe that's not enough for all problems, right? So sometimes you need to play also to increase maybe the number of points in your grid. That makes the calculation more expensive, but sometimes, in particular for calculating properties, that may be important. Then, for instance, spin orbit coupling may be important for some properties, for others not, but I don't know, if you want to calculate like absorption spectra of lanthanides, then you need the spin orbit coupling, right? For sure. So there are many things, let's say, that one could consider. Well, this is just a non-exhaustive list of software for doing computational chemistry. So probably many of you have heard about Gaussian, right? Which is here, which is one of the, I would say, most popular software for, or it's not a software, it's a package, right? Because inside there are many programs that you can run do for calculations. So we will do some exercises next week with Gaussian. And there are many others, for instance, ADF. So that's the Amsterdam Density Functional Package. That's, I think, one of the few that uses Slater type of orbitals. So the software already includes, specific basis set for this package. Amber is more focused on molecular mechanics and molecular dynamics using force fields, but you can also do hybrid molecular mechanics, quantum mechanics calculations. Like for the example I mentioned at the beginning, proteins, right? Maybe you can mix the two methods in different regions of your system. The next one is Carl Parinello molecular dynamics. So that's for you doing ab initio, or maybe not really ab initio, but DFT-based molecular dynamics. So that's a very specific type of method, but you can also do molecular dynamics using DFT with this Carl Parinello approach. But it's bloody expensive. I mean, reaching, I don't know, but one picosecond or 2 picoseconds takes huge time. Well, there are some approximations so that you can extend the time range, but it's still very hard. And I think it's more some specialists that are working with this particular problem. Dalton, that's a general purpose package. Also Gaussian that I mentioned, GAINS is similar to Gaussian, let's say, but I think it's British instead of American, like Gaussian. ROMEX, that's classical molecular dynamics. Jaguar, that's for ab initio, and DFT mainly. MOLCAS, that's a program specialized in multi-configurational methods. That means wave function methods, right? So more than one selected determinant. Like maybe you heard about CAS. So that's the complete active space self-consistent field method. So this type of more sophisticated methods, you can use MOLCAS for that. And MOLPRO, I think same. NWChem is similar. Orca, I'm a fan of Orca, so I'm using Orca most of the time, particularly for, I think if you have metals, Orca is very good, very, very good. So you can incorporate relativistic effects, a spin orbit coupling quite easily, things that with Gaussian you cannot. So yeah, that's my favorite program, is among the ones I know, to calculate properties. Gaussian is more user-friendly for instance, for optimizing geometries and frequencies and so on. Gaussian is perfect. It's very simple to use. So very often I use Gaussian for my optimizations and frequencies, and then I shift to Orca for calculating properties, calculating excited states or NMR or things like that. And well, Spartan and TurboMon, yeah, two more examples. And then there are more programs that well, these are the main ones, I would say. Okay, so yeah, finished. Didn't have many questions, so it was quick. It's only me speaking. So you have any question? Well, by the way, I can send you the presentation if that's useful for you. Yeah. So maybe, how about if I send it by email to one of you and you can distribute it? Okay. You already have it. Okay, that's yeah. So if you can distribute it, that's, yeah, okay, thank you. That's fine. So I hope I've given you like a flavor of what you can do with computational chemistry. I hope it was not, too many equations and so on. Any question or any comment? Well, maybe I can anticipate that. So for next week, I don't recall what is the day exactly, but anyway, it would be great if you could come with your Tuesday. Okay. So it would be great if you could come with your laptop. I will give you a couple of programs, one to visualize and then Gaussian to run, which no, but I have the license for at least for an old version that will work for us. I have version 09 and the current one is 16, but it will work for our purposes. So installing the programs will already take us like 10 minutes at least or something like that. And then we will start playing with simple systems. And I hope you will enjoy it. Okay. Thanks for coming. Thank you.